Good afternoon, everyone. Welcome to week 5. Here we go. We're kind of finally past trees, which is a little bit exciting for those of you who aren't enjoying the trees too much. Though we have some other interesting topics that we'll be going through instead, such as graphs, which are basically more exciting versions of trees in a way. Before we get started, I did just want to point out to you that, as you would have seen in this week's notice, Kevin spent some time on the weekend working on a little thing which is super cool, which you can find in the link here. It starts with Kevin and the dot point. And essentially, there's what happens is that every night now, with your submission, so if you submit your assignment 1 to give, like, because you can do that many times, right? You could submit it tonight, submit it tomorrow, the next night. We actually run in the middle of the night your submission against some really basic tests that we have, right? So like we provided you with some basic data files, we run your work against those tests. So this is not like final tests. I just want to make that really clear. This is not like if you pass these tests, then you get full marks, because the actual testing will be harder and on a more diverse set of data than that. Though you can go and access like to see how your stuff performed every night. So this is usually helpful once you kind of get halfway through the assignment and you've actually like done enough that it's kind of working, maybe not fully, so you can actually get the test run on it. And there's more information here. And then what we do is that we put together a leaderboard. So for every time that if you successfully pass the tests and meet those conditions, then we put you on a leaderboard. And this is like a leaderboard here. So you can see that so far the total user time, and remember that user time is referring to this time here, right? So that's what that user time is referring to. That user time is here, and then there's a name: Playful Baboon, Curious Chameleon, Wise Pigeon, and stuff. And all of those names are here. You can find out your alias by checking the testing output. So essentially, when you go to your submissions page, which is here, and I can't access it, I don't think. Maybe I can. But I don't think I'm a student, so it won't work for me. Oh, Kevin hasn't given me permissions. This is very sad. It won't work for me, so it'll work for you, and this is also where you'll find your alias. So in the actual testing output, so just to be clear, this is where you see your own testing output, which will also have your alias, and then you can see where things fall on the leaderboard. So yeah, that's kind of a fun little thing. It's really exciting that Kevin spent the time to do that and that CSE supports these efforts. So that's super cool. Hopefully it gives you some motivation, gives you some perspective on how everyone else is doing. Caleb says, does the leaderboard form part of our marks, or is it simply for fun? So running tests on your individual submissions is helpful for you because it makes you, like, it helps takes away a bit of doubt, that like doubt you get. You're like, is this fundamentally broken? So you can actually get a sense that like your code will work, it might just be wrong. That's kind of why the submissions is really useful, like a sanity check. The leaderboard is just for fun. So the leaderboard's just for like fun. Kaustub says, is there a way to track memory taken as well instead of just time taken? No. But that's okay, because as we said, like it's extremely difficult for you to actually use an excess of memory in this kind of time frame. It's just not possible. So, well, it's just beyond difficult. Like you'd have to be categorically malicious to do that kind of thing. So no, there's nothing about memory. Yeah, big thanks to Kevin. And I think that's it. Is there a way to change your alias? No. Sorry, if you're humorous starfish, you are stuck being humorous starfish. There's nothing you can do about that anymore, and I'm sorry. Well, these are randomly generated names. There's like libraries that do this kind of thing. So your alias is your alias. What's the best alias here? I'm gonna go with energetic llama or humorous starfish, because I don't know what a humorous starfish like. I don't know how this could be funny, given that it doesn't even have a brain. Anyway, that was just a quick note at the start of the lecture. If you do have questions about that, about the specifics, just post on the forum and Kevin will keep an eye on it because he built it. So yes, now let's get into this week's content. So this week we have a lot to cover. I don't know what first time I've taught this, lectured it, so I'm not sure if we'll need to flow into next week or not. But this week we're really talking about graphs. Graphs are a new type of data structure. Like you learn linked lists, you learn trees, now we're learning graphs. And just like those other topics, we're going to talk about what graphs are conceptually at a high level, like at an abstract data type level. Then we'll talk about how to implement graphs, like what are the different ways you can actually build the ADT underneath the hood. And then we'll talk about how to actually run algorithms on graphs. How do you actually use them to solve problems? And I think this is an interesting thing because with trees we talked about some things you can do with it, right? Like it's an efficient way to kind of do lookup, but it's a little bit boring in a sense, you know? It's like, okay, it's very primitive, whereas graphs are actually used to solve very high level problems. Like, you know, take Google Maps, for instance. Like, how do you think Google Maps maps out an entire city and draws lines between them? That's using data structures that we're about to go through. So today we're starting with graph basics. That's the kind of 5.1 lecture we're at the moment. And the basics of the graph basics we're referring to as a graph ADT because we're really learning about a data type, which is a graph. So as I just kind of said, graphs are pretty, sorry, there's an old piece thing here. There's always a mistake. Why is this one so early on? Graphs are one of the most general and fundamental data types in software. They're used kind of everywhere. So many problems can be conceptualized as a graph. And what's more important is that in a lot of ways, trees are a type of graph and linked lists are a type of tree. So graphs are really, in many ways, like the super type that everything kind of inherits from. So if you can understand a graph, you can understand a lot of linked data structures in the world of computer science. So firstly, a graph which we would define as G, so capital G is what the token we'd use to refer to a graph, is made up of a set of vertices and a set of edges. Now, at a glance, you'll notice this looks kind of like a tree in the sense that you have nodes, or what we call vertices, and you have, you know, children or next nodes, or anything which we call edges, which are connections between those nodes. So you can see that on this little diagram at the bottom here, we have V1, 2, 3, 4, which are our set of vertices, or, you know, that set of vertices is like a collection of items, it's a collection of nodes. And then we have E, which is a set of edges, which is, again, a relationship between all of those different nodes. One of the main differences, I guess, between trees, which is maybe your reference point at the moment, is that with graphs, there is a possibility that there are cycles. That's one thing in trees we didn't have. There was never any cycles in our trees. You could never kind of get caught in a loop. You'd always have to kind of backtrack to move around the tree. You couldn't get caught or only heading in one direction. And graphs don't really have any sense of order. You know, trees, like binary search trees, are kind of ordered. You know, that's kind of why they're useful. But graphs don't really have a sense of order. So they're kind of naturally very unordered structures. If there's any kind of order you want to derive from them, it's normally like after you get data from the graph, you might order it. But the graph itself has no sense of order. So there is no kind of inherent start point like there is in, say, a tree, right? Like a tree has a root, and that root's always where you start from, and it helps shape the ordering of the tree. But in a graph, there is no real intrinsic starting point or ending point. It's just a graph. Now, again, the cool thing about graphs is that graphs are everywhere. Anytime that you have a series of items that have relationships between them, it's a graph. And, you know, I mean, how many things are like that, right? The internet's like that. It's a series of servers connected via, you know, cables and other kinds of network connections. Roads and maps, as I said, are graphs where like every vertice, like vertice. I don't know if that's the right English expression. That should probably be vertex. It's vertex and vertices. So that should either say vertex or vertices, but it's like vertices are intersections and edges are roads. As I said, trees are also like graphs because they're essentially just nodes and edges. The special thing about trees is that a tree is actually just a graph with no cycles. So if you have a graph where there's no cycles in it, where you can't kind of get lost. Like I'll show you this. If you take a graph like this, and we put it in Paint, and I get rid of a couple of edges in particular, like let's get rid of this edge, and let's get rid of this edge. I've removed any cycles from this graph, right? So this is now a tree. So a tree is just a special type of graph where there's no circles, and a binary search tree is a special type of tree that has a particular set of ordering. So you can kind of see how these things are all kind of related. Yes. So, and linked lists are a type of graph where every vertex only has one child. And, you know, circular linked lists, which you might have worked on, I think you worked on that in the lab, or some sense of queue. It's like, they're all special types. Everything is really a graph, because a graph is such a general structure. Nodes and edges, like nodes and connections, vertices and edges. Social networks, your personal network, like humans, are all related via a graph. Everything's just a big graph in life. Now, in reality, as I said, you might, like, graphs are something you might feel like you can work with more concretely, because when it comes to binary trees, it was all like, oh, we're going to sort some numbers or something. Whereas with graphs, it's actually like, here is a problem we might have, where we actually have all these cities, Adelaide, Brisbane, Canberra, Darwin, Melbourne, Perth, Sydney, and we want to answer questions about them, you know? We want to like learn about how to get from Adelaide to Canberra, or, you know, what's the quickest way to navigate, what's the quickest way to drive between all Australian cities and use the least fuel. Like, that sounds like a really interesting problem that would have actual relevancy to the real world, right? So a table like this with all this information is actually just a graph represented in a different format, where all of your cities are nodes and all of the distances between those cities are also nodes. And if you were to draw that graph, it might look something like this. You might have all of your cities, Perth, Darwin, Brisbane, Adelaide, Melbourne, Canberra, Sydney, and they might be mapped like this, where you have all these lines between them, and, you know, you have distances between them as well. And that's when you can ask those questions, like, what cities are connected directly to Darwin? Is there a way to get from Brisbane to Perth? You know, and like, there is, yes, but you kind of, in this case, say you might have to go through Adelaide or go through Darwin. In reality, that's not the case, but that's kind of how you might represent something like this. Now, in terms of the terminology we use when it comes to graphs, there's just a couple of key words. We've already talked about vertex and edge in terms of nodes and links, so hopefully those ones make a lot of sense. But a couple of more interesting things are, sometimes when we look at a node, in a tree we look at a node and we say, what's its parent and what's its children? In a graph, you look at a node and you say, what are its neighbors? So in a graph, any edges that come out from a node are called its neighbors. So in this graph here, V2 has 3 neighbors, which is V1, V5, and V3. And neighbors are any 2 nodes that are directly... Neighbors of a node are any other nodes that are immediately adjacent. That means it's just like one step away. So V4 in this graph has 1 neighbor, because V5 is the only node that is adjacent to V4 here. And sometimes we use other terminology like incidences. So we sometimes will say an edge is incident on V1 and V2. So if you have an edge, like B, that's the name of this edge, then you might describe it as incident of the nodes it's on either side of. And then the last kind of key terminology point is degree. So the degree of a particular vertex, which is a node, remember vertex and nodes are the same thing, is the number of edges incident, is the number of neighbors it has. So all these terms are somewhat interchangeable, but in this case, so the degree of V5 is going to be 4, because there's 4 nodes that are incident to it, there's 4 nodes that are adjacent to it. V5 has 4 neighbors. Oh, sorry. Yeah, you're right. B is incident on... That's wrong. That should be D. Yeah, so everyone's... It's like there's a glitch in the matrix. Yeah, so B here is incident on V1 and V5. Sorry. What's actually incident on V1 and V2 is A. So yes, that's just a slight typo there. So the good thing is everyone's understanding it. That's what's really important. So yes, it's incident, adjacent, edges, neighbors, these are all the same way to describe things next to each other, and degree is simply how we describe, how many edges it has. So, yeah. Now, in terms of, again, more of the terminology, I love Brits. Brits is my favorite person in the world. In terms of graph terminology, there's another 3 really important kind of words that you need to understand that expand beyond the immediate adjacent pairs, right? So with graphs, you might say you have all these like edges and incidences and whatever, but quite often when we look at graphs, we're interested in like how to get from one node to a node further away and go through a series of nodes. So these ideas are firstly a path. A path in a graph is essentially a sequence of vertexes where there's like, it just draws like a line. So it's kind of like taking a graph and just drawing a line through it. So if you say had a graph like this one here, you could have a bunch of paths. So this could be a path. This could be a path because it's just vertexes joined by a single line. This could be a path. This could be a path. This could be a path. This could also be a path. So it's really like a linear run through a graph in a way. And a cycle is essentially a path where the last vertex and the first vertex is the same. So this is a path. Sorry, so to be clear, this is a path. This is also a path. And this is a cycle because I finished where I started. So path, this is also a path. This is also a path. And then this is a cycle. And then the length of a path is just the number of edges in it. And that makes total sense. Like if you have a path like this, what's the length of it? It's 3 because you kind of have to do 3 hops, 3 edges in that path. So we started off with terminology on edges and nodes, and then we looked at terminology on kind of paths through a graph. But if we look at actual graph terminology, 2 interesting types of pieces of terminology with graphs. So firstly, a connected graph is a graph where there's a path from each vertex to every other vertex. So the graph on the left here is a connected graph. And I know you might look at this graph and say, oh, okay, that looks really standard. I don't really know what connected means. But the reality is that a graph data structure does not require all of the nodes to actually be linked. So it's totally valid to have a graph like this. So this here is a graph. It's a series of nodes and edges. There's nothing about a graph definition that says the nodes and edges all have to be connected. You could have a graph that's just a series of nodes with no edges between them. So a connected graph is a graph whereby you can start from V1 and find a path anywhere. And you don't have to think, I don't think about a connected graph in that definition. I just think about a connected graph as like a graph that's not made up of little mini graphs, right? So this graph's made up of 2 mini graphs, or what we call a subgraph, 2 subgraphs, which is like there's 1 subgraph and there's 2 subgraph. So a connected graph is one that's just like this, where you're like, oh, it's all together. Now, a complete graph, which you very rarely see, though sometimes we might use it to represent some problems, is a graph where there's an edge from every vertex to every other vertex. Now, again, you have an intuitive sense of this because I would imagine that all of you, at some point in your life, thought it would be fun to sit down and draw a bunch of circles like this and try and join every single circle to each other. Right? We've all done this at some point. Except better than that. So that's what a complete graph is. It's essentially a graph where there is a connection from... Really? No one's ever done that? You ever just sat down and just drawn little circle, like not anything, just drawn lines between things? I don't know. I don't think I'm that weird. Anyway. It's just one of those like, doodly things that, I'm sorry, I don't want to make people feel silly if they haven't done it. I just imagine a lot of people kind of do the same stupid things. When you like color things in on a piece of paper, like you'd just be sitting there bored in class and you'd just be like, oh, it's time to color in this void space and waste my ink. Just that kind of stuff. So yes, that's what a complete graph is. Quite often complete graphs aren't actually like natural graphs. Quite often complete graphs come from where you say have a set of data, like you know, like say you have a bunch of cows. I don't know why you have a bunch of cows, but say you have a bunch of cows and you're like, oh, I've got all these cows in the paddock. Here's cow 1 and cow 2 and cow 3 and cow 4. And I want to figure out what's the optimum way to like get between all the cows on like a totally open field where there's no constraints. You might actually represent this problem as a graph and say, oh, I'm just going to go and connect all the cows together like this. So you might actually build a complete graph like this, so that you can essentially, I probably missed one, but so that you can essentially like map out all possible trajectories. Because you could imagine, like if you think about Facebook as a graph, then with Facebook you might have, you know, you're here and your friends are here and their friends are here, and then you have other friends here. So maybe you have these two friends and this friend has that friend, and then this friend has like this friend, but they're also friends. Like Facebook is not a complete graph, because otherwise everyone on Facebook would be friends with everyone on Facebook. So complete graphs are often like less representative of some actual network that exists, and it's more like a chance for you to create a system where you can explore all these different permutations. Yeah, tame stationary cows are very tame. They have no velocity in any direction. More graph terminology. So we know what a tree is. A tree is I referred to it before as a graph with no cycles, but more formally, a tree is actually a connected graph with no cycles. Because you could have a graph with no cycles in it, and it could look like technically speaking, this is a graph with no cycles in it. But it's not a tree, because the graph has to actually be territorial. Territorial. Megagrog, you've ruined my sentence by reading your comment. A graph has to be connected, because if a graph isn't totally connected like this, then it's not a tree. So trees have to be connected and have no cycles. So that's a slight complexity in what we had before. And let's just look at this diagram here. So the first one is a tree on the left. We know what a cycle is. That's the red one. Then we have this notion of a spanning tree, which will become a bit more relevant next week. And a spanning tree is essentially when you take a graph and you build a tree out of it, except that tree contains all nodes in the graph. So, for instance, if you take a graph like this one here, like ignore the red lines here, this is a tree in a graph. This is also a tree. You know what I mean? Like if I was to take a subset of the graph, that's also a tree because it's a connected graph with no cycles. However, a spanning tree needs to include all the nodes. So this is not a spanning tree because it doesn't include 8. But you know, this is a spanning tree because it includes all the vertices in that tree that we're making. So that's why this spanning tree here is a spanning tree, because it's a subset of the graph with all of the vertices part of the tree. And then we already know what a path is because we talked about a path. A path is kind of just like a linear line through a graph. And then the last one we have is really weird, which you never really use, which is a click, which is a complete subgraph. So a click is like a part of a graph that's like, remember how we said completes when all the edges are joined? So this graph here is not complete, this green one, because 16 and 13 are not linked. If 16 and 13 were linked and 16 and 15 were linked, then it would be, and then 14 and 17 were linked, then it would be a complete graph, I believe, because everything's linked, right? However, if you take a subgraph that's complete, it's what we call a click. So a click is a subgraph that's complete. So this here is a click because this little graph here, this mini graph with 3 nodes in it, all the edges are connected. So that's what a click is. I've honestly never really found any real life benefit to this personally, though I don't work extensively with this kind of stuff. So that's why this one is that's why this one would be a click if there were then all the lines between them. So pretty much in a graph, any 2 adjacent nodes could also be considered click because this here is technically a connected complete graph because all the nodes have edges between them. Yes, so trees can't have cycles. Vincent said, so is the tree on the left a spanning tree? I think so. I mean, yes is my gut reaction. I can't see why it's not, unless I missed something obvious. I mean, it's a tree, and it spans all the nodes in the graph without cycles, and it's a connected graph, so yeah, would be a spanning tree. Is a single node a complete graph? James says yes. Yeah, so I mean, it's like a lot of these things in the world of maths, because I mean, we really are. This is kind of a very computer science discrete maths topic. Yes, a graph with one node is a complete graph because it satisfies the conditions. Jed says, so three nodes cycle must be a click. Yeah, so if you have three nodes and they're in a cycle like this, that's a click because it's a graph. It's connected. It's complete. It's a complete subgraph of a graph. So to be clear, the spanning tree is just the tree without the black bits. So the reason it's highlighted green is because the point is that if you forget the green for a second, all the edges in this tree are a graph, right? Forget the green. That's a graph. But a spanning tree of a graph is when we just look at the green lines. So we say, okay, I'm going to ignore some of the edges here. And I say, this is now a spanning tree. So that would be a spanning tree of a graph. And that has no cycles in it because you kind of can't just get caught in a loop anywhere. Like, yeah, you can touch the same vertice twice and stuff. You could go up and around, but you're always backtracking. So that's kind of why I think about cycles as cycles are essentially any time you just get caught in a loop moving in the same direction. So yeah, I could like come down here and then there and then there and then back, but I'm backtracking. But this one I can just keep going around in a circle. Same with like here, I could keep going around in a circle here. Whereas like this, I can't really do that. So Gorb says, does it matter what lines you take off or just as long as there's no cycles? So essentially, we're going to learn next week about what we call minimal spanning trees. So it's like any tree that's a subset of a graph that touches all the nodes is a spanning tree. But some spanning trees are more useful than others, which is what next week's content's about. Last slide, which really gets into, I guess, this spanning tree thing slightly more. So, because I think we talked about spanning trees. We did talk about spanning trees a little bit. Yeah, just here, sorry. Tree containing all vertices. So more formally, a spanning tree of a graph is a subgraph of G that contains all the vertices and itself is a tree with connected and no cycles. So, when I say next week, I mean week 7. Yeah. So that's a more formal definition of a spanning tree that we saw in the other slide. Now, a spanning forest is a subgraph of G that contains all of the vertices and is a set of trees with one tree for each connected component. So, spanning forests are really applicable when you're dealing with non-connected graphs. So you'll see here that it's talking about a set of trees that are not connected. And I'll show you a spanning forest example in a second. Though again, just to touch on the questions that have come up a few times, what's the difference between the tree, the green one, and the blue one? So essentially, let me just get rid of some noise. So the difference between these are both spanning trees, right? And they're both trees and they're both spanning trees. This was also a tree. So if I wanted to, I could go and take this and I could say, yep, this is also a tree. That's a tree. It's not a spanning tree of this graph because it doesn't touch everything. It doesn't touch every vertex as part of its tree. The only kind of difference between these two is that in this case, the graph itself is a spanning tree. And in this case here, the graph has a subgraph that's a spanning tree. Because the thing, again, you got to try and get your head around is that this here is a graph. Okay, this is a graph. But then when I take only the green sections, it produces another graph. Or a subgraph, we might call it. But this subgraph is a spanning tree. So that's the kind of language there. Okay. So a spanning forest, let's imagine for a second that these two disjoint graphs form a graph. So this whole thing here is what we call G, right? So this whole thing's a graph. It's not a connected graph because you can't form a path from every node to every other node. So it's not a connected graph. However, so you can't form a spanning tree with it, right? Because a spanning tree is defined as like a subgraph of G that is connected and contains all vertices, right? Without cycles. So in this case here, there's no way I can draw like a spanning tree which like connects everything because there's a big void here that I can't cross. So it's not possible to get a spanning tree in this graph. It's just not possible. However, I could make a spanning forest. And you think about what is a forest? Well, a forest is a collection of trees. So therefore, a forest is just a collection of spanning trees. So if I can get a spanning tree in each of my disjoint subgraphs, then I have a spanning forest. So the blue line here is a spanning forest because I've created a subgraph that's made up of a collection of trees, multiple spanning trees. Well, I shouldn't call it, yeah. Multiple trees that themselves span each separate subgraph. So a spanning forest is only applicable in like these connected areas. Yep. Now, in this week and stuff, we'll be talking about a very particular type of graph, and then we'll be complicating it as we kind of go through later lectures. The two things I just want to flag now, because I'm going to get questions about them if I don't flag it, are that when we're dealing with graphs, there are often two things that we do quite regularly. And the first one is we often give our edges a particular direction. Now, this doesn't make sense for things like social networks, like Facebook, but it does make sense for things like city maps and roads, where lots of roads you can go both directions on, but some roads you can only go one direction. You can only go one way. You know, that like think about Google Maps. You can't always, when you click the reverse arrow to like swap the trip directions, it sometimes gives you a different path because roads are only one direction sometimes. So quite often we're dealing with graphs that have edges with a sense of direction, right? Not both directions. And then quite often we're also dealing with graphs where there's, like the Australia map we saw earlier, there's a weight on the edges, where there's an actual cost to go from 0 to 1 and 1 to 2 and 2 to 3 and 3 to 4. So, because in the real world, it's like, if you're in Adelaide, the time it takes you to get to Sydney is very different from the time it takes you to get to Perth, even though those two things might be connected. So this what we call weighting on edges is something that also plays into it. Now, point is, again, we're not talking about this till, I think, week 7. So for now, all the graphs we work with will both not have weights on the edges and they'll both not have arrows. So they'll be like these graphs, where every edge is essentially a uniform cost. It's like every edge is like, oh, this is just an edge. Doesn't matter. I have no semblance of like what, what direction this is. Sorry, there's like no cost. It's like, yeah, 14 to 13 is one step, 13 to 17 is 2 steps, and I can move in either direction. So we will be talking about that later, but not at the moment. Now, the last thing we'll talk about before we might take an early break is a graph ADT. So we've talked all about graphs in a conceptual sense, and probably in a sense that you're familiar with if you've done Math 1081, discrete mathematics. However, in this course, we're all programmers, so we're actually going to learn how to do some of the coding of these things, and part of that involves building an ADT, just like trees, where you can create a graph, destroy a graph, insert an edge or vertex into a graph, delete a vertex or edge from a graph, and also search it, like look for stuff in it, look for a particular edge or look for a particular vertex. Double slide. So here, this is what a basic graph ADT in C looks like. Now I've removed the header guards from this for the slides, but you can always, of course, do the if and def define and the end if at the bottom of this. But it's not too dissimilar from a tree in the general format of, like, we've got some type defs, and then we have a graph series of functions. Now, you again don't need to know how a graph is implemented to do some of these. This one is pretty standard. We have a graph type name, which effectively refers to a pointer to a struct graph rep, which is an incomplete type. It's something that we haven't implemented yet. That's what we go and implement in the .c file, just like you had the struct for the tree. Okay. We have a type def for int for vertex. Basically, we're just creating this type called vertex, which refers to an int. Could be anything. So if you wanted to have a graph of doubles or chars, you could just change that. And then we have another type def, which is a struct edge. Now, you might be thinking this seems like it's breaking abstraction here, because you're kind of used to the idea of, oh, your actual concrete type defs that actually define the struct, they're normally meant to be in the .c file. But we still actually have other structs there. This will make more sense as we look at the implementations next. But essentially, we still need to, at a high level, define the edge in the ADT so that people can work with it. Because the way this ADT is written is that we can create a new graph, which will malloc a new graph, and it takes in an int for the size of the graph, like how many vertices can you have in the graph, say, or how many edges. I think this one's vertices. Then we're going to have a function called edge insert, where we're going to insert an edge into the graph. Then we're going to have another function called edge remove, where we remove an edge from a graph. And then we're going to have a function that we give it two vertices. Oops. And we ask it, are these two vertices adjacent? So we give it the graph and the two vertices we want to check if they're adjacent. And then we can print the graph and we can free the graph. So quite straightforward functions. However, this struct here is simply to avoid, like if I just take this for a second and we dump it into, how would you put it? There we go. If we like dump, oh, that's not it. Don't do this to me. Not today. Great, so, oh God. So, weird. So we have a file like this, right? And naturally, you could kind of be like, oh, I will just like my graph edge insert makes sense to have a graph, and I'm going to insert a new edge between vertex and vertex. And your remove one would be, I want to remove an edge between vertex and vertex. So you could do something like that. However, the problem is, how do you insert an edge between two vertices if the vertices aren't even in the graph? Well, you could have some pretty weird behavior where, you know, you say, if I try and insert an edge between these two vertices, then I want to create one of the vertices, but that's not necessarily great. So, you know, then you could have another one that's like graph vertex insert, where you insert a vertex. There's a few different ways you could define this ADT. There's no like universal best way to do it. But the particular approach here is to simply say, okay, you just think about a graph as like a series of inserting edges and removing edges. And when we insert an edge, we simply give it a struct that contains the two vertices. So it's kind of very similar to passing in two vertexes. It's just that we're abstracting that into a little struct here to make the code a little bit nicer. Yeah, so that's the ADT for the graph. Now, we're going to spend some time implementing that ADT with a few different methods. That's what we're talking about next. And that's about it for the moment. I know it's a little bit early, but here's the feedback QR code for this lecture. We'll take a 5 or so minute break after I answer a couple more questions. But yeah, if you could do some feedback, then we'll take a break and we'll get into it. I'm just looking at some of the questions. So, Waleed says, I think the reason there's no solo vertex insert is to avoid being able to make a disconnected graph. Yeah, that would definitely be a reason. I mean, this is not, again, unlike a tree, you would see a bunch of different implementations of a bunch of different definitions of a graph ADT. It would be very different in other languages too that use objects, unlike C. So, yeah, but yes, this prevents... I don't even know if this prevents disconnected graphs, because you could just insert... So the problem with an ADT as well is that we give you this after we've given you a lot of context about a graph. So you're coming at this ADT with assumptions about its behavior, but in reality, an ADT like this would come with a substantial amount of documentation that actually says things like the preconditions and the postconditions, and the edge you insert is only valid if one of the two vertices is already in the graph or something like that. But this will make more sense as we get into the implementation side. I'll check out the graph implementation slides. Birds are so loud today. If they're not working. Jed says, so this ADT, it means we already have a vertex to insert into the node. Yes. So that means that we create the vertex outside of the graph, and then what we're actually doing at the graph is just creating edges in the graph. And then we're just inserting edges into the graph with a vertex on either side. Cool. Okay, let's take yep, that's it. So thank you for the feedback as always. I hope I actually put enough rows in I probably didn't even include it in the survey. I'm really worried about... Oh no, it's there. Good. Okay. I probably worry about this every week, but great. I've got Graph Basics and Graph ADT there. I actually combined those two lectures. I might have to update. Screw it. Anyway, if you fill out either of Graph Basics or Graph ADT, it's fine. I'll just combine them together. So, great. Okay, let's take a break and get back to it soon. So, thanks everyone.